In the previous video, we looked at this surface xy times x minus 2 times y plus 3, and we found these 5 critical points: 0, 0, 2, 0, 0, minus 3, 2, minus 3, and 1, minus 3 halves. And now I would really like to know which is a saddle or a minimum or a maximum. And this can be done by using the discriminant d. So this d thing, evaluated at ab, is the second x derivative times the second y derivative minus the mixed derivative squared. To do this, obviously, you need to differentiate everything twice. And then if the discriminant is negative, we have a saddle. If it's positive, we look at the second x derivative. And if this is positive too, we have a local minimum. If that is negative, we have a local maximum. And if the discriminant is 0, the thing is inconclusive. So I think what we have to do is rather straightforward. We take the derivatives we derived in the previous video, differentiate them once more. So these were the derivatives I derived earlier. And now I need fxx, fyy, and fxy. Let's do that. So fxx, I differentiate the x partial derivative again with respect to x. X appears only there, so this is just 2y, y plus 3. Fyy, so I take the y term, differentiate by y again, so this is 2x, x minus 2. And now I need the mixed one, f of x, y. So I take the x thing and differentiate by y again. There's a product rule now, because y appears here and here. So then this is 2, y plus 3, x minus 1, plus 2y. And now differentiating the bracket, y plus 3 gives a 1, so just x minus 1. So then we have common factors. 2, x minus 1 are common factors, and there's a y plus 3 and a y, so it's 2y plus 3. And this is the mixed derivative. Let me summarize on the next page what we have. So these are all the partial derivatives I found, and then the discriminant is f(x), fyy minus fxy square, and I have 5 critical points, like listed here. So now for all these terms, I need to sub in all the 5 points and compute this d for all these 5 points. So let's do that in this table here. Okay, so if I set in the first point 0, 0, then the discriminant becomes minus 36, and the x derivative is 0. If I sub in 2, 0, I get minus 36. Actually, for the first 4 points, I get the same discriminant always, and the same fxx term also. Only for the point 1, minus 3 half, the discriminant is 9, and the fxx term is minus 9 half. So, what does this mean? We learned earlier that if the discriminant d is less than 0 or negative, we have saddle points, so then these are all saddle points. The last one, the discriminant is positive, so it gets more interesting. And the derivative is negative, so then this will be a local maximum. Okay, that's all we have to do. So find all the 5 critical points, find all the second order derivatives, make this strange d thing, and compute the values. Let's have a look how this function actually looks like. So I use again Wolfram alpha. You can just plot in this simple comment here. Here you see the surface, which is plotted. It has clearly a maximum in the middle. This would be the point 1 and minus 3 half. And then it has saddle points, which are right here and down there and there. The 4 saddle points. And the 4 saddle points have the same values for the discriminant, and they look very symmetric. They look basically the same. Here is a contour plot of the same graph. And then here where my cursor is the maximum. And then where these intersections are of the level lines, these are the saddle points. So in the contour plot, you can see the saddle points much nicer, whereas in the surface plot, you can see the maximum much nicer.